Okay, so let's continue our discussions related to this particular course, Introduction to Electronics. So today we'll look at circuits which contain capacitances and inductors. So in the last few lectures, we were mostly looking at circuits which consisted of resistors and dependent sources. Capacitors and inductors are important elements of circuits, and so let's begin our discussion. And so let me start with a statement. All of you are carrying billions of capacitors in your pocket. All right, so it may seem surprising. So we'll see how that can be true towards the end of the lecture. All right, so let's start with some applications. So here is a blood pressure measuring device, and all of you are familiar that to measure the blood pressure, you put a cuff on the arm here and you pump in the air into it and you stop the blood flow, and then you gradually release the pressure, and the doctor then monitors through a stethoscope when the blood begins to flow, and by analyzing that particular data, one is able to determine the systolic and diastolic pressure here. So suppose you would like to, there are automatic blood pressure machines. So suppose you would like to automate this particular part here. So as part of that, you would put a pressure sensor to monitor the pressure that is there in the air pressure that is there in the cuff. So we were doing some experiments in a lab, and this is the data that we had. So in this case, what has happened is that the air has been pumped in, and then the pressure is being gradually released here. So this is pressure as a function of time here. Pressure is being measured in millimeters of mercury, and the pressure data collected by a sensor. So the sensor collects the data and converts it into an electrical signal. And this electrical signal, we have converted it back into a pressure. And this is the data. This is the raw data collected by the pressure sensor. So from this data, if you want to do automatic blood pressure measurement, you have to look at certain features. When does the blood begin to flow, right? So we need to analyze this particular data and determine that. And so if we look at the data, let's look at the data in the initial stages. So initially, the air has been pumped into the cuff here, and pressure is high and no blood is flowing. So we start off from a pressure of around 160, 170 or something, and then gradually we release the pressure here. And there are features in this particular data here. So if I examine it in the early time interval, this is the data that is there here. Remember, so what is being done is the pressure is being gradually released. And this is the pressure measured by the sensor. So you can see a lot of noise here. Of course, pressure is steadily reduced, but you see a lot of noise here, right? And not much one can notice. Well, if I go, let's say, to longer time periods, 16 to 20, this thing here, you can really see a structure here. So you can see a variation in pressure. So systolic part where the pressure is high, and then the diastolic part where the pressure is low, and you can see a periodic signal here. This is how, you can count, by counting these peaks here, you could count for example, the pulse rate, right? So this is towards, when the blood is steadily flowing in the artery, then this is how the pressure signal looks like here. So you can see the signal clearly here. Of course, there is noise also. But what is of interest is to measure the systolic pressure. When does the blood begin to flow, right? To measure that particular part. So in that, we have to go back not to very early stage and not to very later times when things have sort of settled down and blood is flowing in a regular manner. So we need to go back and look at the signal here. So this is where not much is happening, and somewhere the blood starts flowing and you start seeing periodicity. Maybe somewhere here one could see a periodic signal maybe coming here, right? But so what you're seeing is that there are three kinds of time variations. Maybe we need to, perhaps this is the place here at around 110 or so, or maybe a little higher here, is where blood is beginning to flow and one can see some periodic signal appearing here. So maybe the systolic pressure is probably maybe 110 or so, but to make sense of the data, and especially in a automated manner using an algorithm, we need to clean up the signal. There is a lot of noise in it, right? And so what we may do is, so this is the signal that is coming in. The signal that I'm showing is coming in from the pressure sensor. So what I need to do is I need to filter it. Filter in the sense that I need to, let's say, remove the noise that you see here, and I need to remove also this variation that is there, pressure variation that is there here from 125 to 105. That is also not necessary. We need to focus on the signal part here, the periodic part here. And so we need some filtering to occur here. And after filter, maybe some amplification and all that, and then you could convert it into analog to digital. And then after that, you could send it to a display device or with some more processing displayed here. So note that you can see variations over 3 different time scales. There is this pressure variation, slow pressure variation from 125 to lower here. Then there is a fast variation, which is the noise here. And then there is this periodic variation that I said is because of the, the systolic blood pressure and diastolic blood pressure, the pumping of the heart. All right, so what we are seeing is that, in order to interpret signals, what you may need to do is filter the signal or remove certain frequency components and maybe enhance certain frequency components. So when you want to do that electrically, you need a frequency sensitive element. Now, resistors are not frequency sensitive. Resistor responds instantaneously to every signal, V equal to IR. If V changes, I changes instantaneously. But capacitors and inductors don't respond instantaneously. They have a time response. So they are very useful for implementing filters. And so they become essential elements. So what I'm trying to show through this example is that, the signal that you may capture may contain, besides the signal of your interest, may contain noise and other things, and you may want to remove those things. And to do that, you will have to employ filters, and filters would invariably contain capacitors or inductors. They would be almost like essential parts of many of these filters that are there. Now, this noise filtering, this is a slightly complicated signal. Noise filtering I can illustrate through a simple example. Let's say this is through simulation. So let's say you have a noisy signal here. You can see this very sharp variations that you see here around noise, but you can also see that there is some periodic signal. There's a sinusoid here. So it's a periodic signal immersed in noise. So I can take so this is the signal. Now I can take a very simple circuit that you are familiar with, simple resistive capacitive circuit here, RC circuit here. And I can pass this particular signal, apply it as an input, and then I look at the output. And look at what this simple circuit is able to do. Right? It's able to reject noise to a large extent, and now you can see the sinusoid which is there here. Even now it's still noisy. Still you can see that, yes, you can see the periodic signal, you can measure its frequency. You could tell maybe what its magnitude is going to be, but you could filter it even better. So if you understand how this simple RC circuit works, you could adjust the value of R and a C and filter it better. So let me show you a better filtering. See, with the proper choice here, now you can see that the sinusoid is much cleaner as compared to. So note that the original signal is embedded in lots of noise, and by using a capacitance along with a resistor, so a capacitive circuit, we are able to clean up the signal and extract the signal of interest here. And this is an expanded view of the signal. The signal that you see here, this is an expanded view here. Right? So look at the amount of noise that is there here. And the reason why we are able to do it with a capacitive circuit is, all of you may recall, we'll just see today, that capacitance, the voltage across a capacitance cannot change instantaneously, which means that capacitor in this particular manner will have, the voltage across the capacitor will have difficulty following the rapidly following part here, right? And the slowly varying part, the capacitor is able to follow. So that's the principle behind filtering. The fast variations in voltage that you apply here, the capacitor is not able to follow it. While the slower variations, the capacitor is able to follow. Okay, because for a capacitor to follow something, the capacitor has to charge and discharge. And the charging and discharging of a capacitor, you would remember, would be controlled by how much current can flow from here, because the current has to supply charge and the current is controlled by R. So if you don't have enough current, then, or if the R is high, then what will happen is the capacitor can only follow the slower signals, and the faster signal the capacitor will not be able to follow. And that's how the signal gets cleaned. The high frequency noise components, they get rejected, and the signal of interest then remains here. So we're seeing a very important role that the capacitor is playing here in signal processing. Let's look at a different example. We all use our mobile phones and many other appliances which work on DC, and we know that the power that we get from our outlets is sinusoidal power, and the reasons for it, which we will not go into. So we have in AC, and we would like to convert it into a DC. That's what our many of the appliances that we operate, they require a DC here. So a very simple circuit. Don't worry about it. We'll see these things in more detail here. Right now, we are just trying to highlight some of the places where capacitors play a very important role. Just a few capacitors are there almost everywhere, but just a few places. So here, when I apply an AC and we put it through a diode. So we put it through a diode and we have a resistor here. What we get is, this is, some of you may recall, the diode acts as a rectifier. So you have an AC here and the diode rectifies it. So we only get the positive cycle here, right? We get a positive cycle, but we want a DC. We want something which is constant, right? So this has rejected the negative part of the waveform, which is good, but we want it to be a constant value here. So for that, note that again, through simulation, one can illustrate that. So let's say we have a diode here, and this is the waveform that you get, right? And then all I did was put a capacitor across it here, a capacitor of a certain magnitude, and look at the waveform now, right? The waveform, the output here has become constant, right? So we have gotten a constant voltage. We applied a sinusoidal here, and we've gotten out a constant voltage, which is what we desire here. So again, the principle is the same. The capacitor is not, the value of the capacitor chosen is a fairly high value. So the capacitor is not able to, once it charges up, it's not able to respond to further changes here that you see here. And so it stays constant. Simple explanation for it. A more detailed explanation we'll see later on when we look at diodes and look at diode circuits. So capacitor plays a very important role. Well, more than that, more than all of those examples that we looked at, the fundamental principle underlying modern electronics is charge and discharge of a capacitor. Without a capacitor, without its charging and discharging, almost all our devices would fail. Well, why is that? Well, almost all the electronics that we see here, they're all based on a transistor called, we have talked about it earlier briefly, called MOSFET, metal oxide semiconductor field effect transistor. Now that's the topic of our second module in this particular course when we talk about semiconductors and amplifiers and all that. But today, while we are talking about capacitors, so I want to highlight how capacitors are important from a MOSFET's point of view, and how charge and discharge of a capacitor is so fundamental to operation of modern electronics. So I'm going to describe MOSFET, at this stage in a very simple manner here. So a MOSFET, as its name indicates, is metal oxide semiconductor. So let me construct a MOSFET. Let me warn you, it's a very simplified picture of a MOSFET. More detailed description will come later. So we have a metal here, a metal plate here, and then we put oxide. We put an oxide, which is an insulator, and then we have a semiconductor, okay, metal oxide semiconductor. So we put silicon here as a semiconductor. Right, so you can see that this is a capacitor. The capacitors that you're familiar with are two metal plates, and in between is a dielectric, right? So on one side we have a metal plate, we have a dielectric. On the other side we don't have a metal plate, but we're using semiconductor, okay? So it's a slightly different kind of a capacitor here, but it's a capacitor nevertheless. The silicon acts as one plate and the metal acts as another plate. Let's put two contacts here on this side of the silicon and this side of the silicon here. And right, so it's still a capacitor, and then this is one terminal, let's say, This is another terminal, and this is the third terminal here, right? So, and let's give them the name here. So this is called the drain of a MOSFET. This is called the gate of a MOSFET, and this is called the source of a MOSFET. So don't worry too much about it. The origin of the names will come to that later on. Okay, so gate, drain, and source. And let's, it's an electrical device, so let's add some voltages. Okay, so we add a voltage here between, so we use source as a common terminal. We add a voltage between drain and source, and we add a voltage between gate and source here. And let's call them the drain to source voltage. S is just a common terminal for us. So drain to source voltage, and this is the gate to source voltage. All right, so what is so special about this MOSFET? How does it work? Well, I've already said that this acts like a capacitor, right? And so we have applied a voltage here, and note that between these two contacts there is a semiconductor, silicon. So if charges are there in the silicon, then when you apply a voltage across it, the current should flow here. So what happens is, we'll not go into the details. What happens is when you don't apply any voltage, let's say this is 0 volt here, the number of electrons in silicon is so small here, and the current is very, very low, almost negligible, right? So when you don't apply any gate voltage, VGS is 0, hardly any electrons here, and practically no current. I'll show you some real data a little later on, right? 0 current. Then you apply, let's say, a voltage of 3 volts. It could be 3 volts, 5 volts, even, depends on how the MOSFET is constructed. Let's say we apply a voltage of 3 volt. So note that 3 volt is here and is applied here, and this plate, because of the source here, let's say this is ground here. So this is like at a lower potential as compared to this, okay? Because 3 volt is applied between gate and source here. So this side is lower and this side is higher. So it's a capacitor. So when you apply a positive potential, what happens is you create positive charge here, and a capacitor requires negative charge here. So what happens is you have negative charge here, and these negative charge is due to electrons. So when you apply 3 volts, let's say here, because of the capacitive action, you create a sheet of electrons at this particular place here. So now you have electrons here, and then when you apply here, now the current begins to flow, right? It's no longer 0 current. It has now a much smaller resistivity, and the current begins to flow. Not only that, if instead of 3 volt you apply 5 volt here, you would expect more charges here and more charges here, and the current would be even higher. On the other hand, if instead of 3 volt I put 1 volt here, well, the charge would be smaller here, and number of electrons would be smaller here, and current would be smaller here. So what we are seeing is that this drain current is being controlled by gate voltage here. And if we don't apply any gate voltage, well, we will get 0 current. So we are able to control this drain current through this gate to source voltage here. And so what you are seeing here is something that we had talked about earlier, is a voltage control current source. Okay. Now I'm not justifying here why between drain and source is acting like a current source here. Okay. So it's acting like a current source plus some resistor here. At this point, all that you can see from here that you have something like a voltage control current source kind of a thing here, right? Because the current flowing between drain and source is being controlled by the gate voltage. How? By the capacitive action. This forms a capacitor. As you increase the voltage here, as you increase the charge here, the number of electrons increase, and thereby the current increases here. So in a MOSFET is an example of is a voltage control current source here. All right, so let's continue. So we are saying that the capacitive action or a capacitor is a fundamental part of a MOSFET. Okay, and this is the symbol that we use for a MOSFET, right? So gate here, and the gap between the two indicates, say, insulator here, and there's a drain and there's a source here. The arrow is used to differentiate between which one is source and which one is drain here. So it allows us to highlight that. Now, as I said, this part was a very simple picture of a MOSFET. This is a more realistic picture of a MOSFET. And if you're having difficulty on relating the two, maybe I can turn it at an angle here, like this. So maybe now you can see here, this is the metal here, this is the metal here, there is silicon dioxide, there's silicon dioxide, and silicon here is a p-type silicon, and the contacts are being made here and here. Okay, don't worry too much about it. We'll come back and discuss this in more detail later on. Okay. All right, so we said drain current is controlled by gate voltage here, right? So that's the property of transconductance that we see in the MOSFET here. Let me show you some real data. So this is an actual MOSFET that was measured, CD4007. This MOSFET is an IC with several MOSFETs in it. So this was the data measured in a lab. So drain current versus gate to source voltage. So you can clearly see that I can control the drain current by gate to source voltage here, right? So you apply a larger gate voltage, you get larger current. Why? Because you have larger number of electrons. Why do you have larger number of electrons? Well, because of the capacitive action. You applied a higher voltage across a capacitor. Naturally, you have more charge on both sides, right? So that's the principle here. And here what is happening is it's appearing as if the current is zero, but the current is not really zero. You cannot see it on this particular scale. You could see it more clearly on a log scale. So if I put it on the log axis here, and this is linear, you can see the current dropping here. So when I apply 0 volts here, or very close to zero, there is very, very small current. As I said, these are actual measured currents. So I have a current of around maybe 10 picoamperes or so, current flowing between drain and source. So these are not perfect insulators, and even if I don't apply any voltage across this particular capacitor, the silicon is not a perfect insulator. It's not an insulator at all. So it has some residual charges. So there is some current flow here, okay, but it's very small. It's only when you apply significant gate voltage that you get significant current flowing here, right? Okay, so we can do some interesting things. So now I'm going to use this particular symbol of a MOSFET. So we can do some interesting things with this particular MOSFET here. So let's construct a simple circuit. So this is the MOSFET, gate, drain, and source. We have attached a resistor here, connected it to a supply voltage here, VDD, drain supply voltage because it's connected to drain VDD here. And let's apply some input voltage here, okay? And remember, this MOSFET has this data here. This is the data that we saw here, okay? So let's construct something useful out of this particular MOSFET here. So we put here, let's say we use a supply voltage of 5 volt. And for the sake of discussion, let's say I choose the drain resistance as 1.5K, okay? So with these values, now there is a MOSFET whose characteristics is given here. I've chosen 1.5K here and a supply voltage of 5 volt, and a circuit is complete. And we would like to see how this circuit behaves when I apply different values of Vin, input voltage. So my interest is in the relationship between Vout and Vin here. So suppose I apply 0 volt. If I apply 0 volt, so I'm here at this particular point here, and as I said, the current is in picoamperes. So when picoamperes flow through 1.5K, the drop is negligible, and the output voltage is going to be practically 5 volt. So when we apply 0 volt, I'm going to get 5 volts at the output, okay? So now you can see where I'm going. You apply a low voltage and you get a high here, high voltage here. So, all right, now let's remove it. Let's apply a high voltage here, 5 volt. So when I apply 5 volt here, you go back 5 volt here and you have currents in milliamperes flowing. Let's say 3 milliampere flows here. Or something like that. So if I have 3 milliamperes flowing here, and 3 milliamperes multiplied by 1.5K would be around 4.5 volt. So 4.5 volts drop here. So what will be remaining is about 0.5 volt here. So if it's a little more than 3 here, so the voltage here would be less than 0.5 here. So what is happening is I've applied a high voltage at the input, and what do I get? I get a low voltage at the output here. So this acts like an inverter. If you recall, what is a digital inverter? You apply a 0 here, you'll get a 1, and you apply a 1 here and you get a 0. This is exactly what is happening here. If I apply a 1 means a high voltage, 5 volt, I get a low voltage here, 0 here. And in the previous case, when I applied a 0, I got a high voltage here, 5 volts here. So this is how a very simple construction of an inverter, of a inverter or a NOT gate, right? NOT gate through use of a MOSFET and a resistor here. Now let's see two inverters connected in series. You know, in fact, when you build logic circuits, you don't just use one inverter. You may convert an inverter to a NOR gate and an AND gate and many other things. So let's say we have two inverters connected in series. Suppose we apply a signal like this here. So initially it is 1 and then goes 0. Well, we know what will happen at this output. When it is 1, the output should be 0. When it is 0, the output should go 1. So it should go like this here. And because of 0 to 1, the output here will go 1 to 0. So that's how the signal propagates, okay? But this is where we are only talking in terms of high and low, right? So let's construct this two-way inverters. So we could do it like this here. We just saw a MOSFET with a resistor as one inverter here. And the output of this one is connected to the second inverter here, okay? So these are the two inverters. And let's look at not in terms of 1 and 0s, but in terms of voltage, what really happens here, okay? So when I apply a high here and low here, right? So when it is high here, you would expect this output to be 0 here, low here. And then when you switch it to low value here, the output should go to high value here. So the output should rise. And the output rises like this here. The output does not go instantaneously up like this here. It rises like this. And why does it happen? Well, note that the output is initially 0, right? And then it has to go to a higher value of 5 volt. Now, as it goes, what happens is between the, we showed here, there is a capacitor here, right? So between the gate and the source, there's a capacitor here. And the capacitor has to be charged. And who is charging this capacitor? Well, the current is coming from here, RD. So there is an RC circuit, R here and a C here. C is a part of this. And because of this charging, the voltage here, the output does not go instantaneously to a high value. It doesn't go from 0 to 1 immediately. It takes certain amount of time because of this time constant here. R and a C here. Capacitor takes some time to charge, so it charges gradually. So what you're seeing is that there is a delay. All my NOT gates and more complicated gates, they all have delays in them. They don't respond instantaneously. You may change the signal instantaneously here. For example, I may go from 5 volt to 0 very abruptly or sharply, but the output of it will go slowly. Slowly means it will go over a certain time period. And why does it go over a certain time period? Well, it's basically because of charging of capacitance. Similarly, if it were high and you wanted it to go to low, well, it will also discharge through this, through the, for example, the MOSFET. It may discharge through the MOSFET, and the MOSFET also has resistance in it. So both charging and discharging they result in delays. So all my circuits that I have, all my complicated, let's say adders, subtractors, microprocessors, all of them have delays in them. There's a certain speed at which they work. And the fundamental reason there is a speed limit to all of this is basically because of capacitance charging and discharging. So the speed of the circuits is eventually limited by your RC circuit, a capacitor charging and discharging. And from there, you can also realize, capacitance, all of you know, is capacitance value is proportional to area. So you would think that if I make my MOSFET, if this capacitance is coming because of the MOSFET, if I make the size of the MOSFET smaller, capacitance being proportional to area, well, capacitance will become smaller, and therefore the charging will become faster. And so this is the reason why, one of the reasons why scaling of transistors. If you make the transistors smaller, the circuits, they become faster. Right, so simple examples, but they're illustrating important concepts of why is there a delay in any of the circuits. And so in almost all the circuits that you would encounter, all the digital circuits that are there, the delay comes about because of charging and discharging of the capacitors here. All right, so capacitance, we all know. It consists of two plates and with a dielectric in between. The dielectric could be anything, air, polyester, many kinds of dielectrics are there. All right, some very simple concepts associated with a capacitor. So we have a capacitor here. There's a current I and a V and a charge here. So I'll go very quickly. All of you know it. Q equal to C times V. Q is in coulombs, V is in volts, C is in farads. I equal to dQ by dt, the relationship between current and charge. So we can apply that to this relationship. So we get I equal to C dV by dt. So that's the fundamental current voltage characteristics of a capacitor. I equal to C dV by dt here. And of course, we could write it as V in terms of I as an integral. All right, so the other thing we know is when there's a voltage across a capacitor or there's a charge stored on a capacitor, there's energy stored which is equal to half CV square. So that's also something that you've all seen before. The other thing that we note here is that for DC or steady state, we use the word steady state, which means steady state means voltages and currents are not changing with time. So if you have a voltage across a capacitor which doesn't change with time, then dV by dt is 0, and then I equal to 0 here. So which means that the capacitor under steady state acts like an open circuit, right? Zero current is like an open circuit. Okay. We also know when you take 3 capacitors or more in parallel, the capacitors, they add up, C1 plus C2 plus C3, just the opposite to a resistance. If you have capacitors in series, well, the capacitors add up just like resistors add up in parallel, 1 over C1 plus 1 over C2 plus 1 over C3. All right, so let me come back to the point that I made, that all of you are carrying a billion capacitors in your pockets, okay? So in what sense is that true? Well, let's look at what we call as a DRAM, dynamic RAM memory. So all of you carry your mobiles, and the mobile now has 6 GB RAM or a 8 GB RAM, 8 gigabytes or 6 gigabytes of RAM here. And this RAM is what we call as dynamic RAM. Okay. So if you take a computer or a mobile and you examine it, well, you'll find that there is a microprocessor here and there's a memory here. And this memory is what we call as dynamic RAM memory here. So you buy phones with a certain value, certain amount of RAM that is there. Now, if I go inside a RAM, in a DRAM, what I find is that it's a memory. DRAM is a dynamic random access memory. So the basic storage unit, so it stores information as a digital number, as a binary number 1010. The basic storage unit is a capacitor. Okay, so let's look at it in a little bit more detail here. So if you have a capacitor here, and if there is a charge greater than a certain amount, right, and if charge is greater than a certain amount, let's say a certain amount of charge here, we can call this as a logic 1 or a digital 1. And when the charge is less than certain amount, for the sake of discussion, we can say, let's say 0 charge. So 0 charge, obviously it's 0 voltage here, we can call it a logic 0. When there's a sufficient amount of charge on this capacitor, so the voltage across it will be Q by C. And if Q and C is, are reasonable, then the voltage across the capacitor would be high, and we call it logic 1. Right, so you store a 0, a binary number 0 or a 1 by storing charge on this particular capacitor. If there's no charge stored on the capacitor, well, there is a 0 stored on the capacitor. If there is a certain amount of charge stored on the capacitor here, certain reasonable amount of charge, the voltage is high, and you have a logic 1 stored in the capacitor here. So zeros and ones, the binary numbers, the data in the form of binary numbers, are stored as charges on capacitors, right? So when you have, let's say, 4 capacitors here, well, you can store a binary number 1101, right? So you can store a binary number 1101. How do you store that? Well, you store charge on this capacitor, don't store any charge on this capacitor, store charge on this capacitor, and you have a number 1101, right? So 1101 is in binary is 13. So how is the data 13 stored in a DRAM? Well, it's stored as a charge on this particular capacitor here. All right, so let's go a little bit deeper into this. And each capacitor basically stores 1 bit of information. So the charge on this capacitor could be 0 or could be non-zero, and therefore this particular indicates whether this value is 0 or 1. So 1 bit of information is there on one capacitor. So one capacitor will provide you with 1 bit of information. So if you want to make a 6 gigabytes of memory, well, 6 gigabytes of memory will require 1 giga is 10 to the power 12, 10 to the power 9. So 6 gigabytes would require 6 billion capacitors here. So when you're carrying your mobile with 6 GB of RAM, well, you're carrying 6 billion capacitors around. these capacitors are of course very, very small in size. And so let's go a little bit deeper into it. Okay, so how do we store data into a DRAM, and how do we read data into a DRAM here, right? So we do that by using a transistor. The MOSFET that we just studied, we use that as a switch to charge and discharge a capacitor, right? So for example, I want to charge up this capacitor, store a 1. So what I will do is I will apply a voltage to the gate here, and the gate will turn my MOSFET on, and the gate, the MOSFET acts like a switch, sort of a low resistance switch here, and 2.5 volts will go and charge up this capacitor. So MOSFET acts like a resistance, and if I give it sufficient time, the voltage 2.5 volt will charge here, and I will get 2.5 volts here. Okay. On the other hand, if I apply 0 here, well, no matter what was stored on the capacitor before, if there was 0 earlier, then nothing will happen. 0 will go through here. 0 will go through here, through this here. If on the other hand 5 volt was stored here, or 2.5 volt was stored here, the capacitor would discharge. The capacitor would discharge, and eventually 0 volts would be stored here. So we can use a transistor. You'll see why we require a transistor. You may be wondering, why can't I just charge up the capacitor directly? Why do I need a transistor? You'll see in a minute. When we have billions of capacitors, how do you charge and discharge? So we require a transistor for that purpose here. So the point is, we can store whatever we want on this capacitor. We can store 2.5 volts, we can store 0, meaning we can store a 1 or a 0. Okay. All right. So when the transistor is off, when you don't apply any voltage here, the transistor we saw, when you don't apply any voltage, there's a very, very high resistance, or there's very, very low current here. So the capacitor will discharge, but it will discharge very slowly. So, but if you leave it for a long enough time, your memory, the capacitor would lose its charge, will get discharged here, will lose its charge. That's why we call it a dynamic memory. So, you need to refresh it from time to time. If you just store charge on it and leave it, well, the charge will leak away, and you will lose the memory here. Okay. So why do we require transistor switches? Well, we have billions of capacitors in our overall memory. How do you write a data into the memory? How do you read the data out from the memory here, right? So let's say you have these billions of capacitors here, and they're all arranged, let's say, in this particular manner here. Now you want to, and all the bits are stored on these capacitors here, right? So you want to access this particular bit here. You want to read what is the data here. So to read the data, note that read the data, you will have to have a wire connected here, and it comes out here. If you want to read this particular capacitor, you will have to wire come. Remember, the data has to be read from the memory and maybe sent to the microprocessor, sent to the printer or somewhere else. So to access these, so let's say there are a billion capacitors here. And so to read the data, you would require these billion wires coming out, which obviously sounds ridiculous, right? This memory, if you have a chance to examine, memory is an IC, and you have, pins that are there, maybe 100, 200, 500 pins or something of that sort, depending on the capacity of the memory here. So you would have that many pins that are there, very limited in hundreds, the pins that are available here to connect it to a printer or a microprocessor. So we don't have a billion wires here, right? It's obviously impossible to run that, but we do have billion capacitors here, right? But then how do we access it? How do we access the data stored here? Oh, and in the problem is also, how do you program a particular capacitor? How do you select a capacitor and put in a certain amount of charge into it, thereby storing a 1? Or if 1 is stored on a certain capacitor, how do you access that particular capacitor and discharge it so that a 0 is stored here? Well, that's how do we do that? So basically, you cannot have that many wires coming out. We said wires are in only, let's say, hundreds. So let's say there is one pin that is coming out for the memory. And through this pin, let's say you want to read all of these capacitors here. Either program them or read the value of these capacitors here. So if we directly connect it, well, then you're shorting all the capacitors together. And if 1 is stored here and a 0 is stored here, they'll all mix up and you lose the data. So obviously you can't do that. So if you're trying to access all these capacitors through one particular pin, what we do is we put these transistors as switches. Right, so now what we can do is the following. If you want to access a particular capacitor here, what you do is you turn up this transistor on. If you turn this transistor on, then what happens is this capacitor gets connected to the pin. And all other transistors are not connected. They're all off. So all of them are isolated, but only this one gets connected here, right? So transistors are used to provide selective access from a pin to a particular memory element. So let's look at this concept and expand it here, okay? All right. So this is how, in a simple case, we are showing how memory is organized. So we have a capacitor here on which 1 bit of information is stored here. And this capacitor is connected to a transistor. And it's arranged in the form of a matrix, right? It's arranged in the form of a matrix like this here. So note that we have, let's say 1, 2, 3, 4, and we have 1, 2, 3, 4. So we have 16, let's say, bit memory. And for 16-bit memory, we require only 4 lines here and 4 lines here, 8 lines here. Now, we can easily show that for a large memory, the number of lines required externally would be, when we come to binary numbers in digital, very small number of lines here. Anyway, we'll come to that later on. So how does it work? Well, let's say you want to program. You want to program, let's say these capacitors with these values, 0, 0, 2.5, 2.5, which means 0, 0, 1, 1. Well, how do we do that? Let's say we want to do with this one, with this row. So we put 0, 0, 0 here. So when we put 0 here, all the transistors are off. Note that 0 volt is going to the gate here. 0 volt is going to, all the transistors are off. Only this row here is provided with 2.5 volts. So all these transistors are on. All these transistors are on. So when you apply 0 from here, this 0 goes here and the transistor is on. We'll program it to 0 volt here. When you apply 2.5 volt here, this 2.5 volt is going everywhere, but these transistors are off. So this 2.5 volt will go here. This transistor is on because its gate is connected to 2.5, and we'll program it here. So that's how you can program from an external point of view by selecting a row. One row of bits you can select and program them. 0, 0, 2.5, 2.5. Right? And that's how they get programmed. Well, if you want to program some other row, you could select this particular row here, and you could program this particular one here. 2.5, 0, 0 here. So this is 1, 0, 0, 1. So that way you can program any of these rows that are there, and you can access them with much less number of external lines are in hundreds here. Okay. What about reading the memory? So reading is also same. Let's say the data is stored here. So if you want to read what is the data stored in this particular row, you enable this particular row here with 2.5. So what happens is this 2.5 here then becomes available here, and 0 available here, 2.5 here. So you can read it also through at this particular part here. All right, so what we have shown you here is that the memory, the DRAMs are basically the memory unit is a capacitor. And the transistors are used to provide access to a particular bit of information for programming them to be on or off, and also for reading the data here. All right, so obviously, if you make capacitors small, you can, the capacitor is the basic unit of memory, so you can pack in more number of bits into a particular area. And also the charging and discharging of a capacitor, for writing a particular bit into a capacitor, it takes certain time because of the transistors also have resistors here. And if you make the capacitor small, the charging will take place faster, the discharge will take place faster, and the memory will become faster there. Okay, so we'll stop here. And the point was to emphasize that capacitor is a very fundamental unit, fundamental element. And without the capacitor, the modern electronics, because the principle of operation of a MOSFET is based on capacitive action, the memory DRAM cells are based on capacitors, and the charging and discharging of capacitors is an important phenomena. So we'll look at that in more detail in the next lecture. All right, so let's stop here.